Hello guys, nice to see you.
Good afternoon.
Hi. Hope your weekend was good. Any questions on conservation of momentum, which we actually finished to discuss last week, like linear momentum? Yeah, our next topic will be rotation of rigid bodies. And I guess during this week, we are going to work on that. So I believe so far we don't have questions, and still people are joining. Who is interested? We can proceed further in our discussion and start this new topic, rotation of rigid bodies. Okay. Then let me switch. Okay. Yeah, so rigid body means we already don't operate with a mathematical point, or which when we neglect with its dimensions with respect to the distances it travels. And this body stays constant in shape, so it doesn't deform. So it's ideal rigid body. So in this particular section, we are going to discuss rotational motion of rigid bodies. So let's maybe consider some rigid body which rotates around axis O, which goes perpendicular to the plane of our image. And taking into account that rigid rotation of rigid bodies, during the rotation, we don't move the body in the space itself, like whole body stays in the same position. However, different parts of this body, so if we consider different points, let's say A and B, they will, and this rotates counterclockwise, they will rotate with different linear velocity. So these parts of the rigid body will move in space, and that's why they will possess some, in particular, also kinetic energy. So in total, the rigid body will also described by some kinetic energy of rotational moment. And since different parts of this rigid body, which rotates about a fixed axis, will possess different linear velocities, depends on the distance of these parts to the axis of rotation. Rotation of rigid bodies requires some a bit different approaches to be described than regular translational motion of bodies and particles. And that's why it is defined in a separate chapter, which we are going to start discussing now. So let me delete this, and we will consider some reference line, like some horizontal line. It is convenient to describe position of different parts of a rigid body which rotates in a polar system of coordinates. So if we pick up some point, I don't know, let's let it be P. The distance of this point to the axis of rotation will be R, radius, and the position of this point will be defined by angle, so it's defined by the length of this radius and angle theta with respect to some reference line, which usually is horizontal line. Then we can write that when this body moves, then what happens, this particle P will move about the axis of rotation, follow some circular motion, which we actually considered before as a particular case of motion in kinematics. So that's why initially we will just recall certain parameters which describe this circular motion. So the distance, so here we can draw in a bit larger scale so it's more clear. This is our radius, this is our point, here is our angle theta. So the distance it travels, let's call it S. It's path of this part of the rigid body. Oh, sorry, it's not R, it's P. Point P, and here we have radius. So the path S is equal to the product of radius to the angle theta. And from here we see that theta, this angle, is defined as the ratio between path and radius. So theta is measured in radians, so the units of angle theta for the polar system of coordinates, it is measured in radians. And if this point P starts at 0 time at this reference line and makes a full rotation, so it comes back to initial position, then this theta, let's call it total, is equal to 2 pi r, which is length of this circle, divided by r. So we cancel out radius, and will be 2 pi radians. And then, of course, you can operate with some parts of this full angle, 2 pi radians. It's either 1/4 pi or 1/2 pi radians, and so on. Okay, so we define the position in polar system of coordinates of some particle, a small part of a rigid body which rotates about some fixed axis. Now, definitely we need to proceed further and get some parameters which describe the change of this position. So first of all, it's angular velocity. So if we operate with some average angular velocity, it will be initial theta angle. Then, oops, sorry, it's in, so it will be final theta angle minus initial angle divided by final time minus initial time. And of course, we get delta theta divided by delta t. So this is about average angular velocity. For sure, we need to operate with instantaneous angular velocity. Then this one will be considered as a limit of delta t approaches 0, delta theta over delta t. And this is d theta dt. So it's first derivative of the angle theta over independent variable t, which is time. Okay. The same we can write for instantaneous acceleration, angular acceleration. So we write A is equal, again, limit delta t approaches 0, delta omega delta t. So angular acceleration means how fast we change the angular velocity. And this is first derivative, oops, sorry, not of velocity, angular velocity. Of angular velocity over time, or it is equal to the second velocity of theta dt squared. Now you see that we have three parameters, theta, omega, and angular acceleration, which have analog parameters in translational motion. So it's when we are talking about one-dimensional motion, it's x, it's coordinate. Then we have linear velocity v and acceleration a. So that's the different approach for rotational motion in order to address the features of rotational motion. That's why we, instead of these parameters, operate with these parameters, which are defined in the polar system of coordinate, assuming that every point, every small part of the so why it's useful? Because every small part of a rigid body which rotates about a fixed axis possess the same angular velocity and angular acceleration. However, since it depends on the radius, they will have different linear velocity and accelerations. That's why, in order to have a uniform approach to describe rotational motion of rigid bodies, we operate not with their coordinate linear velocity and acceleration, but with theta, angular velocity, and angular acceleration. Okay, so far we were talking about only absolute values of angular velocity and angular acceleration. And these are just magnitudes of respective vectors, because definitely these parameters are vectors. And now let us figure out how we define the orientation of these vectors. So it's a bit different from more intuitive vectors of linear velocity and acceleration. So there is only one direction for a rotating rigid body about some axis, which uniformly applies to any parts of this body. And this direction is actually along the axis of rotation, because this body rotates around about this axis. So let us assume we have such a rigid body in the plane of our image. So we have here some axis of rotation O, which is perpendicular to the plane. And now we can define the direction of angular velocity and angular acceleration. So if our body, such wafer, on two-dimensional wafer on this image, rotates counterclockwise, so in this direction, then our angular velocity vector will be directed from the plane towards us. So we can write like this. It means that the vector goes perpendicular to the plane of the image, and it comes from the image towards us. If we change the rotation of spinning to clockwise, then angular velocity vector will be oriented in opposite direction. So this is the sign how we show a vector which is oriented perpendicularly to the plane of the image, but it goes from us towards the plane. So it is always along, so angular velocity vector is oriented always along the direction of the axis about which the rotation happens, and its direction will be changed to the opposite if we change the rotation either clockwise or counterclockwise. So in order to define the direction of angular velocity, very common are two approaches. So one approach is right hand approach, or right thread like rule, or right thread screw rule. So maybe I will try to switch the camera, because for sure that will be difficult to draw. So if we have some rigid body which rotates, then we have our 4 fingers wrapped around in the direction of rotation. Then the right thumb will show us the direction of the angular velocity, like this. So if this is a rigid body, it rotates in this direction, like from here to here. Then this is the when we wrap our 4 fingers in the direction of rotation, then perpendicularly to this plane, we will have our angular velocity vector for this particular case. If this body rotates from here to here, so if you look from top, it will be clockwise, then we need to wrap it like this. Our 4 fingers will be wrapped in the direction of rotation of this rigid body, and our thumb, right thumb, will, like with our right hand, our thumb will show the direction of the angular velocity. Another approach which I mentioned is the right thread screw. So if you consider a screw like normal screw, usually all of them have right thread. So means right thread, that means when we rotate with a screwdriver the screw, its translational motion happens in the direction, like it goes forward. So when we rotate it clockwise. That is the rule how you define the direction of the angular velocity. So if you rotate the right thread screw in the direction of rigid body rotation, its translational motion of the screw will show you the direction of the angular velocity. So it will always fit with coincidence with the direction of angular velocity, which is determined by this approach of right hand. So there, yeah.
May I ask a question?
Yes, sure.
Why the angular velocity is not in the plane with other, like with the rotational velocity and others?
Okay, yeah, it's a good question. So that is the point of going from coordinate and linear velocity to angular parameters, because when we have a translational motion, even if we have some big body, when we don't neglect with its dimensions. When we have translational motion, means from this point it moves to another point through the space. Every point without any rotation. So in this case, every point of this body possesses the same linear velocity vector. So it always the same. If we don't rotate the body and move it just from one place to another, so that is translational motion, then every small part of this big body will possess the same velocity vector in terms of magnitude and direction. However, in case of, and then it's kind of very intuitive and reasonable. However, in the case of rotational motion, when we don't have any translational motion in space, so our body stays in one position and just rotates around its own some fixed axis of rotation, then we cannot describe each part, small part of this body with the same linear velocity vector. Why? Very simple. We have different velocity vectors for velocity vectors. They have the same direction, but their magnitudes will be different. And that depends on the radius. So the further is part of the body from the axis, the higher velocity will be. And in order to have some uniform parameter which uniquely describes the rotational moment, we operate with angular velocity. And there is only one direction which is the same for each. So for each small part of this rotating rigid body, which is direction perpendicular to the direction along the axis of rotation. That's why if we operate with one vector, we want to go from many different linear velocity vectors of all different parts of the body to one single vector. It has to be angular velocity vector, and its direction should be along the axis of rotation, because it's only one symmetric direction for all particles which are moving together with the rigid body when it rotates about this axis. And that's the right mathematical approach to quantify rotational motion of rigid bodies.
Thank you.
You're welcome. Okay, let's come back to our slides. Okay, so we defined the direction and okay, we still need to define direction of the angular acceleration. So we define direction of the angular velocity, and angular acceleration is nothing else as derivative of angular velocity over time. And that's why angular velocity vector will be aligned in the same direction of angular acceleration vector will be aligned in the same direction as angular velocity vector in case of increasing angular velocity. So if we start to rotate around about this axis, fixed axis of rotation with higher over time, the angular velocity increases, then direction of angular acceleration will coincide with angular velocity vector, and it will be in the contrary, also along the axis of rotation, but in the opposite direction to the angular velocity vector if angular velocity decreases. So if over time the rotation slows down, then angular acceleration vector will be in opposite direction to the angular velocity vector. So this is everything what we need to know about orientations of these vectors. And now we need to consider some specific case of rotational moment, the same way as we did it for the translational moment. Do you hear me?
Yes.
Yes.
Okay. Something happened to my screen. I change it, but it doesn't change on the Zoom. That is strange. Let us change back and try again. Okay. No, it just stuck. Oh, something is going on. But now its shape is somehow extended. Strange. Sorry about this, but yeah, let's try to do it like this. if we can still see. So I mean, you can see probably something. So we need to consider the case of uniform rotation. Rotation of a rigid body with constant angular acceleration. So you already recall that we considered this specific case of motion in kinematics when we considered linear one-dimensional motion along one axis with constant acceleration. So for this particular case, we have actually the same set of equations, but they already, in case of rotational moment of rigid body, for a particular small part of this rigid body can be written in this form. So first of all, for velocity, we write angular velocity final is equal to angular velocity, always want to write linear velocity, angular velocity initial plus angular acceleration times t. Then for position, which is described by the angle theta, final angle theta will be equal to initial angle theta plus the product of initial angular velocity and time plus angular acceleration times square divided by 2. So you see that it has the same structure as previously derived equations for this translational motion in kinematics for constant acceleration, linear acceleration. But here we just substitute x and linear velocity and linear acceleration with their parameters which describe rotational motion. And also the other form is valid. The final angular velocity square is equal, again, initial angular velocity square plus 2 times angular velocity times the difference between final theta and initial theta. So in all these cases, this is so-called system of equations, of kinematic equations for a particle which forms one of the parts of the rigid body which rotates about a fixed axis. And that's the way how you can describe its position over time. And another good example, the correlation between theta and x, between omega and v, and this angular acceleration and linear acceleration. Okay, so let us move further and write some equations which give us the relationship between angular velocity and acceleration to linear velocity and acceleration. So let us assume that we have a system of coordinates x, y, and some rigid body, something like this. It rotates about axis which goes through the origin perpendicular to this plane xy and through the origin of the system of coordinates. Let's denote this axis of rotation as O. So we have some point P, like very small part of this rigid body. It has location at distance r from the axis of rotation. And here is the vector of linear velocity of this particle. So we want to get the relationship between linear velocity and angular velocity, which we actually again recall our previous work in kinematics, because we considered some cases of rotational like motion along circular trajectory. So linear velocity will be the ratio between path and like first derivative of path distance it travels over dt, change of time. So we can write that this is equal to radius times d theta over dt. So path is the product of radius to the change of angle theta. And this, since the first derivative of theta over time is angular velocity, we get r times omega. So this is the value of magnitude of the velocity. And we see that velocity, linear velocity, is a function of r, which means that it will be different for different particles. That's what the main message of this discussion today. Now we need to go for acceleration. And in this case, if we consider that this particle does some circular motion, circular trajectory, we have two options for acceleration. We have two components. One will be linear, like tangential acceleration, or also another option, always present for circular motion. It is centripetal acceleration or radial acceleration, which is directed along the radius vector in the opposite direction of radius vector. So let us consider both cases. First of all, let us consider tangential acceleration. A tangential will be, it's equal just to change in the magnitude of the linear velocity. It's derivative, first derivative of linear velocity. And this is equal again to taking into account already these relationships between linear velocity and angular velocity. This is equal to r d omega dt, and this is r a, where a is rotational acceleration, like angular acceleration. So now we also need to write another equation for the radial acceleration, or centripetal acceleration. So let's call it AC. We know that it's related to the linear velocity as v squared divided by r. So now we can substitute. And by the way, do you remember, guys, what is the origin, the reason for this centripetal acceleration or radial acceleration? Is it present? Is it equal not to zero when we have uniform circular motion? Who remembers? Yeah, you see that here for the equation, we don't have change of velocity. It's v squared divided by r. So it doesn't matter if we have change in velocity in the magnitude of linear velocity or not. Yeah, centripetal acceleration originates from what?
Change in direction of velocity.
Yes, from change of the direction. So this is the origin for this acceleration. And in case of angular relationship between angular velocity and in terms of angular velocity, this centripetal acceleration can be given as r squared times omega square divided by r. Then we cancel this square and this r, and we get r times omega squared. So now we have expression for the tangential and centripetal accelerations in terms of angular velocity and acceleration. And what we need to do, we need to get total acceleration of the this particle, because total acceleration is the sum of vectors of tangential and centripetal acceleration, which is like this. So in terms of absolute values, it's equal to, let's call it total, equal square root of total, because we already have AT. AT is tangential acceleration square plus centripetal acceleration square. And now in terms of angular, in terms of radius and angular acceleration and velocity, we can write based on these equations which we got on the previous slide. We have r square a square, because a tangential is a product of radius to angular acceleration, and then we have square plus we had r times omega square for radial acceleration, for centripetal acceleration. That's why we have r square omega 4 force power in force power. So we can factor out this r from the square root. Will be just r. Doesn't look like r times square root of angular acceleration square plus angular velocity in force power. Okay, so this is the relationship for the total acceleration of particle moving along a circular trajectory in terms of radius, angular acceleration, and angular velocity. Try to remember this, because that could be used for solving some problems. Okay, so next point which we will discuss, but I guess we will start really discussing this on Wednesday. Next time it will be kinetic energy of rotational moment of rotational rigid bodies, and that will require introduction of another parameter, which is moment of inertia, and this is analog to mass. So if we define mass as a feature of body, which defines how much this body is resistant to external forces to gain some linear acceleration, then moment of inertia describes how much a rigid body is inertial. It tries to counteract to get some angular acceleration of rotating around some fixed axis of rotation. And it's a bit more complicated than just concept of mass, because for the same body, it will depend on the direction of the axis of rotation. It will not be just one value. So it will be only for a sphere, since sphere is symmetrical in all three dimensions, x, y, and z. Doesn't matter how it will spin, it will possess always the same moment of inertia. However, if we have some disk which is symmetric only in x and y and not symmetric in z, then definitely it will possess different moment of inertia. It will respond to work against gaining some angular acceleration about different axes of rotation in a different way. And that's what we are going to consider and discuss in details during our next class, and try to learn how to calculate moment of inertia of some of rigid bodies of different shapes about different axes of rotation. Okay, if you have any questions, you are welcome. You can ask now. Also can ask at the beginning of the next lecture, but try to just become embrace this concept of set of parameters which describe rotational motion, because we definitely need these parameters, taking into account the unique feature of rotational motion of rigid bodies in comparison to their translational motion. And I think that we quite in details try to discuss these differences during our today's class. And for sure, we will continue on Wednesday. Okay, guys.
Can I ask a question?
Yeah, sure.
Why the centripetal acceleration is equal to radius times angular velocity squared?
Yeah, once. Oh, I just changed, but actually I need to show you previous. Oh, it came back to normal. I don't know what happened with this screen. Okay, so your question was why centripetal acceleration is equal to r times omega squared.
Yes.
Yeah, okay, so it's actually this answer to this question is here. So we know that centripetal acceleration is linear velocity squared divided by r. Before we define that linear velocity, is equal to the product of radius to angular velocity. So if we substitute now this here instead of linear velocity, it will be r squared times omega squared divided by r. We cancel out this r and this square, and eventually we get r times omega squared.
Yeah, I understand that, but then like what before that, why centripetal acceleration is velocity squared divided by r?
Oh, that is actually, we had actually two lectures at the beginning during the kinematics chapter, where we used two different approaches to describe it. One, it was just vector approach to show that centripetal acceleration is equal to v squared divided by r. And another lecture was just based on calculus. We were taking derivative of equation which describes uniform circular motion, and we eventually got the same answer with the direction of this centripetal acceleration. So all these lectures are recorded and they are available on Moodle. So if you go there, you can check and watch through that, and also can double check in the textbook. But this was described and explained in details. We spent almost 2 lectures on this question.
Okay, sorry, thank you.
Yeah, you're welcome. I guess it's just not possible to describe it from scratch. Now, it will be better if you address this recorded video. And if you still, after that, have some question about that, we can discuss it first. It's not a problem. So next lecture, you are welcome to ask if something was not clear. Okay, guys. I think we are running out of time now. And I hope to see you all on next time on Wednesday. Have a good evening and goodbye.
You too. Thank you.
Mhm.
Thank you. Bye.
Bye.
Goodbye.